Bam! Mr. Taru. In this math lesson, we're going to do 4 examples involving basically 2 concepts here. The algebraic definition of a dot product, both in 2-dimension and in 3-dimension. We're also going to be working with the formula for finding the angle between 2 vectors in our last 2 examples. This is going to be a fairly long video because these problems are going to go from a really quite easy dot product situation we have going on here and going on to a pretty challenging 4th example. So that's why I'm going to put timestamps in the description of this video so that you can jump ahead if you don't need the easy stuff, or you can just know when the video kind of ends for sort of more straightforward applications that you may or may not be dealing with in your particular class. But then we don't have to search through a whole bunch of videos trying to find a nice lesson for my entire homework problem. Well, not mine, but yours. I've already done the homework. Given 2 vectors in the plane, vector u, written in component form of either the sum of 2 component vectors or with these chevron brackets your textbook may be using for shorthand in component form, or as the book I'm currently teaching out of, it writes the component forms very often in a column style vector. But we have vector u and v. It doesn't really matter if they're in either 2-space or ultimately in 3-space, but to find the dot product between 2 vectors, you just simply multiply the components along the x-axis, the components that go along the y-axis, and if you work it in 3-space, the components along the z-axis, and simply add that up. And you get some kind of scalar multiple. As I discussed in a previous lesson, developing the idea of scalar product, you are simply, with the dot product, finding really the magnitude of 2 vectors going in the same direction after one of the vectors is projected onto the other. Okay, so for example 1, links to those videos are in the description. Example 1, if vector A is equal to 3i plus 2 times vector j, and vector B is 4 times vector I minus 6 times vector j, and we're going to find the dot product between A and B. Just for notation, this isn't really necessary for this particular question, but we can say vector A is equal to 3, 2. Vector B is 4, negative 6. And then if we want to find that dot product, well then vector A, dot product with B, scalar product, dot product, inner product, whatever your book is using, we have 3 times 4 plus 2 times negative 6, and that is equal to 0. Now, if the dot product comes out to be 0, then that means something special about the angle between the 2 vectors. And if the dot product, even though my properties are in a different video, but you have these couple of properties of dot products. If the dot product is just simply plus or minus the scalar multiple, the magnitude of each of these vectors multiplied together, or if it comes out to be 0, that's going to tell you something about the vectors. Our last 2 examples are going to be finding angles between vectors, but if you pull up this formula, or the geometric definition for a scalar product, dot product, inner product, this alternative form of the definition shows you that the last thing you're doing here is the cosine. It's a magnitude times a cosine of theta. Well, if the cosine of 90 degrees or the cosine of pi over 2 is equal to 0, so if your dot product comes out to be 0, then that's from the cosine of 90 degrees or pi over 2 giving you that multiple of 0 causing this entire dot product to come out to be 0, and thus our first fairly straightforward example, but I wanted to throw something a little special in there, remind you that if your dot product is 0, those 2 vectors, A and B, are orthogonal. Or you may be calling that perpendicular. We just like to use the word orthogonal a lot when we're dealing with vectors. No. The rectangular solid has square bases ABCO and EFGD with sides of 1 unit and is 2 units tall. I could also say that we have a cuboid of ABCO, EFGD with its bases, which are squares, 1 unit long, and is 2 units tall. Okay, so what are the coordinates of the vertices? And then using those coordinates, let's hence find the dot product of vector OF and OA, and the dot product between EB and FC. Hence just means that you have to use information that you were either given or found through earlier parts of your particular question. Well, I don't like doing any geometry problem without a diagram, so let's do that. Okay, so I'm starting off by drawing the the square base as a parallelogram, trying to bring some depth into this picture. Now I'm going to draw some vertical line segments that are about twice the length of this. Try and make those all about the same, and then draw another parallelogram on the top of my cuboid. Do some dotted lines to show that we're looking through this solid. I'll even dot the axis lines. And I just realized, well, it's there because it's on the axis, but let's... Okay, so with this being the x-axis coming out positive as it comes towards you, the positive side of the y-axis and the positive side of the z-axis, that's how I'm going to orient this diagram, or this rectangular solid, this cuboid, just to make this our life as easy as possible. The lengths of each of these sides are going to be 1, and we're going to have a base of ABCO, and O means the origin, so it needs to be down here. EF, GD. This vertice is from the origin, one step out from the origin, no movement left to right, no movement up or down. So that coordinate right there for A is going to be 1 on the x-axis, do not move left to right, do not move up or down. Coordinate B is out 1 and to the right 1. So positive movement along the x-axis, y-axis, and do not move up. Finally with C, not finally, with a lot of points, but don't move towards the left, don't move out away from this plane. Don't move along the x, don't go up or down, just go 1 unit to the right on the y-axis, so, and then finally the origin. Up here at the top of our cuboid, our rectangular solid, we have coordinate E, and that is come out from the origin along the x-axis. There's no horizontal movement, there's no movement along the y-axis. I guess the x-axis is horizontal as well. Hopefully you know this by now, but the x-axis is coming out perpendicular to the board. X-axis, y-axis, z-axis, so misuse of the word horizontal there. But at any rate, step out 1, do not move left to right, just go up again, height of 2, and finish up the rest of those points. All right, now we're going to use these 8 coordinates, 8 vertices, to find the dot product of OF and OA. Well, as we just saw on the previous board, this dot product is going to be looking at, well, let's actually write these position vectors out. So we have OF. So if coordinate F is 1, 1, 2, well then that is vector OF. Same with OA. And your dot product is finding the product of the components along the x-axis, the y-axis, in this case because it's 3-dimensional, the z-axis, and add them. And you get some kind of scalar multiple of 1. We're going to be using in the next 2 examples that scalar multiple, the answer that we get from the dot product, to help us find the angle between 2 vectors. Okay, so here we have to find the dot product between vector EB and vector FC. So we have to remember how to identify the initial point and the terminal point. Of course, the vector notation is starting above E and F, so those are our initial points. So I'm going to keep this in the same order. So terminal minus initial. So 1 minus 1, 1 minus 0, 0 minus 2. That is going to get dot product. We're going to find the inner product or scalar product of that vector EB with FC. So terminal minus initial, 0 minus 1, minus 1, 0 minus 2. And I'm going to kind of just move this horizontally, even though I really do not like work done that way, but I'm going to run out of room. Now, we've got vector EB. We've got vector FC written as column vectors. Let's go ahead and find that dot product. Multiply the components along the x-axis. Add it with the product of the components along the y-axis. And finally, the z-axis. And that is it. Let me just make sure I didn't do something silly. Yep, good. Bam! Example 3. What is the angle between vector OF and FC? Okie dokie. So let's use red. Vector OF is going from the bottom left-hand corner of the base of this cuboid to the front upper right-hand corner. And then from there, we're going to we're looking at vector FC as defined by this rectangular solid or cuboid. So there's our red. Here is our green. Vector FC. Oh, it's so nice to have that off. I do like the sun in my videos much better when the air is not running, but I am in Florida. It is the summer, and I apologize that I couldn't just record all the video without that air running. Would want to look at me though, I'd be a big sweaty mess. Okay, now one thing to remember here, in the previous lesson we said that if you want to find the angle between vectors, that they have to have the same initial point for the context of there being an angle between two vectors. Vectors are defined by the magnitude and the direction, not the initial point. So while you might look at this diagram and see, well, there's an initial point here at O and this other vector has an initial point of F, think of it as you sort of starting, that's just the vectors as defined by this cuboid. Think of it as if you were to just take these two vectors, put them on a three-dimensional graph so that they have the same initial point. I can't call them necessarily position vectors because we have this idea here that this is starting with vector F. But if you draw them both off of the origin, let's just say, they're going to form an angle between those two vectors. And what is that angle? That's what we're going to find out. Well, did you catch that little weird negative sign in front of the two? Yep, miscopied it. Okay, so let's try this again. Shirt's untucked, I'm editing my video, and I'm looking at it going, that looks a little funny. So what is that angle between those two vectors? Well, the cosine of theta is going to be equal to the dot product of OF and FC over the magnitude of vector OF times the magnitude of vector FC. Okay, so let's try and do this without the copy error, sign error if you will. We have the dot product, so we're going to be multiplying 1 times negative 1, adding that with the multiplication or product of 1 times 0 plus 2 times, yes, negative 2. All of that over the magnitude of vector OF. We're going to take the square root of 1 squared plus 1 squared. Try to write 2 parentheses there. Plus 2 squared. That's going to get multiplied to the magnitude of vector FC. So we're looking at negative 1 squared plus 0 squared plus negative 2 squared. Really, you're just going to have a negative sign change up here, and ultimately have to recalculate our answer here. We're looking at negative 1 plus negative 4 is going to be negative 5 here in a second. Over the square root, we have 1 plus 1 plus 4 is equal to the square root of 6. And here we have 1 plus 4, which is 5, is equal to the cosine of theta. So ultimately theta is going to be equal to the inverse cosine of, just making sure I have not, okay, of negative 5 over the square root of 6 times the square root of 5, or if you want to call it the square root of 30, that's fine. 100 and 55.905, whoa, chalk down, degrees. And now back to a regularly scheduled program. No, 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 no. It's the last example. Consider the vectors. Vector u, which is equal to the sine of 2 alpha times vector I minus the cosine of 2 alpha times vector j, plus vector k, and vector v is the cosine of alpha times vector I minus the sine of alpha times vector j minus vector k. Of course, is just written in component form, where you have the sum of your component vectors along the x, y, and z axis. Just trying to write it differently for each of my examples. Get used to the notation. Where alpha is greater than or equal to 0 and less than 2 pi, let theta be the angle between these two vectors. This is a two-part last example, so I guess there's really technically 5. 3 fairly straightforward, and one that maybe isn't as bad as it looks when you read this, because it looks really, really confusing, way more complicated than the last example. But if you just keep your head on straight and remember that we're dealing with vectors and these formulas that we're learning, and we're going to write cosine of theta in terms of alpha, and theta is the angle between the two vectors. Okay, so even though this is a much more complicated looking problem, let's just let the question tell us what we need to do. We have an angle between two vectors. Okay, so the cosine of theta is the dot product between our two vectors over the magnitude of those two vectors multiplied together. Yeah, so hopefully when we look at our components here, sine, negative cosine 1, cosine, negative sine, and negative 1, and we set up this formula, we'll have a bunch of stuff that's just going on and working with this variable of alpha. So the cosine of theta is the dot product, multiply each of the corresponding components, and then add them together. So we have the sine of 2 alpha, cosine of alpha, plus the negative cosine of 2 alpha times negative sine alpha, and then plus 1 times negative 1. Okay. Now let's take a look at the denominator. The magnitude of vector u, which of course I'm not going to be able to find, there's a bunch of variables, but we can write out the formula. We have the magnitude of a 3-space vector is simply square each of the components along the x, y, and z and add them up. So for vector u, keep that first like our notation, we have sine of 2 alpha squared. This is the whole thing squared. We're going to write this in a second. Sine squared of 2 alpha plus negative cosine of 2 alpha squared plus 1 squared. Second vector, a cosine of alpha squared plus negative sine alpha squared plus negative 1 squared, being careful of those parentheses so you have a correct sign here. There's a lot going on here, but it looks like the denominator is going to clean up pretty nicely. This is why this is this challenging question, and as you go through all of your math classes, I'm not sure what level of math you're doing this in here right now. I don't work with problems this complicated, say in a pre-calc class when we first start getting introduced to all of our trig identities, like your Pythagorean identities, your sum and difference identities, your half angle, your double angle. Might be a good bonus question. This is something that I would be looking at with my IB HL math students. generally as seniors, so it's a pretty challenging question. But if you just keep all that knowledge in your head, everything you learn in mathematics is eventually going to come around and come back into play again. As you look at this denominator, you have the sine of an angle times the cosine of another angle. Oh, should clean this up a little bit before I get all excited about working out the next line and talking about trig identities. The negative times negative is going to become a positive. Now I don't want to write so much in the denominator, so I'm going to talk about one nice thing going on here. Never mind. Yes, I will. I'm seeing the negatives being squared, so. Sine of an angle times the cosine of another angle plus the cosine of that same angle that was into the sine function over here times the sine of that second angle. Do you recognize this binomial in our numerator? It's the right-hand side of one of your sum and difference identities that you learned back in pre-calculus. Or maybe you're in pre-calculus right now and your teacher's giving you a nice challenger problem here. This is equal to the sine of two angles added together, the sine of 2 alpha plus alpha. That's cleaning up rather nicely. Now in our denominator, of course, one of our Pythagorean identities, sine squared plus cosine squared, doesn't matter what those angles are as long as they're the same. So it doesn't matter that this is 2 alpha here and 1 alpha over here. Those come out to be 1. So really this is just the square root of, well, 1 plus 1, which is not 1. 2. And same thing here. Cosine squared plus sine squared, that's 1. 1 plus 1 is 2. Now our final answer for the cosine of theta, expressed as a most simplified expression that is only in terms of alpha, is going to come out to be sine of 2 plus 1 is 3 alpha minus 1 over, and the square root of 2 times square root of 2 is simply equal to 2. And I always double check my work because I am terribly prone to making silly mistakes. And let's just add a set of parentheses in here just to clarify exactly what is the angle measure that's going into the sine function. And that is the end of our first part of example 4. The last part coming up right now. No. So now that we just got done creating that equation that relates the angle of theta, the angle between the two vectors, to alpha, we are going to use that relationship to find, hence, use of previous information, find all possible values of alpha on the interval between 0 and 2 pi, including 0, not including 2 pi, for which the angle between the two vectors is equal to 120 degrees. And we came up with this expression through the formula that tells us the angle between two vectors. So let's plug 120 degrees in here and find out what happens. So we have the cosine, I'm pointing over here and then standing in front of it, the cosine of 120 degrees is equal to the sine of 3 alpha minus 1 over 2. Well, we know our unit circle. The cosine of 120 degrees is equal to negative 1/2. So just doing a little bit of multi-angle trig equation solving thing going on here. Multiply both sides by 2. We're going to add 1 to both sides. That's going to give us 0 is equal to the sine of 3 alpha. And if you hopefully remember from trigonometry, as you're solving these trig equations, you get to the end where you have to apply the trig function. If you have a multiple angle that's inside, or a multiple angle that's inside your trig function, that just tells you how many times you have to go around the unit circle. If this is 1/2 theta, or alpha, you go around the unit circle half the distance, or half rotation, pi radians, or 180 degrees. In this case, yeah, my head's thinking radians and my problem's in degrees. I have to remember, keep that in mind as we go through this. We're going to do the inverse sine of both sides. I'm also going to turn this around. 3 alpha is equal to the inverse sine of 0. Yeah, okay. Sine of 0, y values on the coordinate on the unit circle. It's going to happen at 0, pi, 2 pi. Every time you rotate and hit the x-axis, your y coordinate is going to be 0. And I'm going to stop here at 5 pi because if I just keep counting by pi, 0 pi, 2 pi, so on and so on, if I go to 6 pi and then divide by 3, I'll end up with 2 pi, but that's not in our interval given to us that we want alpha to be on. We're almost done. Just divide everything by 3. And alpha comes out to be 0, pi over third, 2 pi over third, 3 divided by 3 is 1, 4 pi over third, and 5 pi over third. So yes, questions involving dot product could very easily come up to an example here in a problem that involves you having to remember sum and difference identities, Pythagorean identities, how to solve some, in this case, a relatively easy trigonometric question. All these things will come around again as you further your journey into mathematics, as far as it needs to be for your degree or in curiosity. But for now, I'm Mr. True. Bam! Go do your homework.